7.1. This is what we want to do. Given the equation of a parabola, complete the square, and then find the vertex, the focus, and the directrix, and then graph the parabola. So this is the beginning of a chapter on conic sections. The reason they call them conic sections is because if you take a cone and you slice through it with a plane or a sheet of paper, you can create all four of these shapes. So if you slice through a cone with a sheet of paper at an angle like this, you get a parabola, and this is 7.1. If you slice through the cone sort of with a horizontal sheet of paper, you get a circle. That's 7.2. If you tilt that horizontal sheet of paper, you get an ellipse, which is 7.2. Which is why circles and ellipses share a lot of similar properties, is because they're the same kind of cut across the cone. Just one is a straight horizontal cut, the other one's tilted. And then if you make a vertical cut, you get something called a hyperbola, which is 7.3. So these are the four types of conic sections that we're going to study. We're going to start with the parabola. And here's a different definition of the parabola than maybe what you're used to. It's the set of all points in a plane equidistant from a fixed line called the directrix. So the directrix is this horizontal line at the very bottom, and a fixed point called the focal point, or the focus, and that is this. So believe it or not, this distance between the focus and the vertex, let's call that P, is the same as this distance, P. And this distance from here to here, maybe we'll call that P sub 1, is the same as this distance, P sub 1. And this distance from here to here, we'll call that P sub 2, is the same as this distance, P sub 2. So if you start out with a parabola and a vertex at 0, 0, and a directrix, which is given by y equals negative p. So check this out. You've got the vertex at the origin, 0, 0, right? And the focal point right here is p units away, p units above the vertex. So if the focal point is p units above the vertex, then the directrix has to be p units below the vertex. It's on the other side of the curve. The same distance, but just on the other side. Yeah, like a reflection. So that makes the directrix. That's this horizontal line. And so the equation of that would be y equals negative p. For example, if the focal point was 2 units up from 0, then the directrix would be 2 units down, negative 2. Get it? Y equals negative 2. You can also do this sideways. And so if you have a parabola that opens to the left or to the right, the same thing happens. Here's your distance p. Well, first of all, here's your vertex at 0, 0. And here's your distance p going to the right. So let's say that's a distance of 3 units. Okay, great. Where is the directrix and what's its equation? Well, the directrix, if the focal point is 3 units to the right, the directrix is 3 units to the left, or x equals negative 3. That would be the equation of the directrix. If we go back one slide, this is important. So this is another way to define the equation of a parabola. X squared equals 4 times p times y. And don't forget, p is the distance from the vertex to the focal point. If you go to the sideways parabola, you'll notice that all we did to make it open to the side is we flipped x and y. Y squared equals something. Find the focus and the directrix of this parabola, and then graph it. So here we have y equals negative 1/12 x squared. And what we want to do here is we want to solve for x squared. Because remember, our equation for the parabola is x squared equals 4py. So what we want to try to do is take the equation we're given and make it look like x squared equals something. So if we multiply this side by negative 12 over 1, and we multiply this side by negative 12 over 1. So here we have y equals negative 1/12 x squared. We're going to multiply both sides by negative 12 over 1. And so we get x squared equals negative 12y. And keep in mind, we want this to look like x squared equals 4py. P is important. Why is P important? P is the distance between the focal point and the vertex of your parabola. It's also the distance from the vertex of your parabola to the directrix, that reflection line. So P is an important number. We need to know what P is. And so now we need to make this part look like that. So we're going to factor a 4 out of everything. So you factor a 4 out of that 12, or you rewrite negative 12 as 4 times 3y. And now you know P is negative 3. So if we were to sketch this parabola, the vertex is at 0, 0. P is negative 3, which means the focal point is 3 units below. This is the focal point right there. It also means that the directrix is on the other side, up 3 units. So your parabola is going to look something like this. So find the equation of the parabola. So first we give you the equation, have you come up with the parabola, and now we're going to give you information, have you come up with the equation. So find the equation of the parabola with a vertex at 0, 0 and a focus at 5, 0. Then graph the parabola. Let's graph it first. So if you've got a vertex at 0, 0 sitting right here, they're telling you the focal point is 5, 0. So that's 1, 2, 3, 4, 5. This is the focal point. So where is the directrix? Negative 5, 0, right? It's got to be on the other side. 1, 2, 3, 4, 5. So here's, we'll call this x equals negative 5. There's your directrix. What does the parabola look like? This is a sideways parabola. The focus is always inside the parabola. So now we need an equation. Remember our equation, in this case it opens to the side, so it's going to look like y squared equals 4p times x. What does p equal to? P is the distance between the vertex and the focal point. It's also the distance between the directrix and the focal point, and in our case it's 5. So the equation would be y squared equals 20x. If we move the vertex off of the point 0, 0, h is a horizontal shift, left, right. K is your vertical shift, up and down. And this is how they're incorporated into the equation. Remember our original equation when we did this was x squared equals 4py. If you look at the point 0, 0, if h is 0 and k is 0, it gets you right back to the original equation. But if they're not 0, you have to put in minus h and a minus k. The same thing is true if you look at a sideways parabola, except for one thing. Remember how we switched the x and the y in the sideways parabola? Well, you also have to shift your h and your k. K is always associated with the y coordinate because it's an up and down shift. H is always associated with x because it's a horizontal shift. For this parabola, find the vertex, the focus, and the directrix. How do you know this is a parabola? It's squared. And then does this parabola open up-down or does it open left-right? And how do you know it's an up-down? Because the x is what's squared. If this y was squared, then it would be a left-right parabola. But the x is squared, so it's an up-down parabola. What we need to do is find the vertex, the focus, and the directrix, or in other words, we need to take this equation and we need to put it in the format x minus h squared equals 4p times y minus k. So somehow we got to take this equation and rewrite it in this format that has a square in it. So how do we write things that have perfect squares? Oh yeah, complete the square. So that's what we're going to do. So here's the original. And what we'd like to do is we'd like to take this 4y and the 5 and kick them over to the other side. Subtract 4y, subtract 5. And now we have a blank. We have a blank here and a blank there. What goes in the blank? Remember, it's b divided by 2 squared. That's what went in the blank when we were running complete the square. So we're going to take the 6, we're going to divide it by 2, and we're going to square it. 6 divided by 2 is 3, 3 squared is 9, so we're going to add a 9 to both sides. And now, believe it or not, you've created a perfect square over on the left-hand side. This now becomes x plus 3 times x plus 3, which is x plus 3 squared. We've also done some arithmetic over on the right-hand side, and then we factored out a 4 so we can get negative 4 times y minus 1. We wanted it to look like this one at the very top. So what is h equal to? H is negative 3. What is k equal to? Positive 1. What's p equal to? P is negative 1. So with this information, can we graph it? Yeah. Where's your vertex? HK. Negative 3. 1, 2, 3. Positive 1. There's your vertex. We'll call that V. What is P? The distance from the vertex to the focal point. Negative 1. So that means your focal point is down here. This is F. And if that's your focal point, that means that your directrix is on the other side, D. So your parabola is going to look something like this. This one opens a little bit differently. Is it a parabola? Yep. Does it open up-down? Not so much. It opens left-right. How do you know it opens left-right? Because y is the thing that's squared. So we're going to run the exact same procedure on this one. So here's the equation. This time we're going to take the negative 8x minus 31 and kick that over to the other side. So we get y squared minus 2y plus blank equals 8x plus 31 plus blank. What goes in the blank? Negative 2 divided by 2 squared, which is 1. So believe it or not, you've now created a perfect square here. Y minus 1, which is y minus 1 squared. We'll take the 31 and the 1 and put them together and get a 32. And then at this stage we're going to factor an 8 out. So we need h, we need k, and we need p. So what is h? Remember, h is a horizontal shift associated with the x coordinate, negative 4. What is k? Uno. And what is p? Remember, this guy here has to equal 4p. Positive 2. So h is negative 4, k is 1, p is 2. Can we figure out what this looks like? Sure. We're going to have a vertex at negative 4, 1. Negative 4, 1. 1, 2, 3, 4. Positive 1. So this is V. That's my vertex. And I know that P is equal to 2. So if I go 1, 2 units this way, that's my focal point, which means if I go 2 units to the left, that'll be my directrix. X equals negative 6. And then what does this look like? Something like that. Coordinates of the focus, it looks like it's going to be negative 2, positive 1. And that's just pulling it off the graph. Looking at the graph. We could go through and calculate all this, but sometimes making a picture and then figuring out where things are off the graph is a little bit easier. Excellent. Applications of parabolas, because they're super awesome. Parabolas are nice because you can have a single focus point, that's F, and if you project rays off of the parabola, they are emitted in nice parallel lines. This works two ways. This works for rays going out of the parabola, rays coming into the parabola. So for example, if you have a flashlight, a really good flashlight or a really good headlight has a very well defined parabolic reflector, and the light bulb is at F, the focal point. So that's for rays going out. What about rays coming in? Your satellite dish. This is your sensor, by the way. The arm on the satellite is the receiver of the signal. And so the beams come from space, they hit this parabolic dish, and they're redirected to the focal point.